Hey guys, I am Gautam and welcome to Chemics. In this video, I am going to talk about thermodynamics. Okay, so it's a very important chapter for CSR, NET, GATE or even IIT JAM examination, and also for your general study and other MSc entrance examination. So you have read thermodynamics from your class 11, 12 standard. Then now it should be advanced thermodynamics and it's about chemistry. So we will discuss about the chemical thermodynamics. Okay. Before we start, I just want to say you that if you are preparing for IIT JAM examination and you want to get some study materials, very low cost study materials and high quality study materials, then you can contact me in this number. Okay, and also you will get the details in the description below. And also if you want to understand the chapter wise videos, okay, then you can get the UNACADEMY videos where I make videos chapter wise, and that will help you a lot for IIT JAM, NET and GATE examination. Okay. So basically, what is thermodynamics? So there is two terms. One is thermo, another is dynamics. So what do you mean by thermo and what do you mean by dynamics? Thermo is related to heat. Dynamics is related to movement. So heat movement. That is when heat transfers from one system to another system or one place to another place. That whatever that system, that phenomena we will discuss by thermodynamics. Okay, so heat movement can be discussed by thermodynamics. This is the meaning of thermodynamics, the word. Okay, so heat, we know heat and movement. So what do heat and movement do actually? Heat and movement generally produces work. That is, work is produced in when heat and movement, that is thermodynamics, gives work. Remember this one. So we know work is a form of energy, heat is another form of energy. Thus heat into work, conversion of work into heat or heat into work, that we will discuss in the that we get generally, that we can see in the nature, in the mother nature and everywhere, whatever we are looking at, wherever we are looking at. So that's why heat is converted into work or work is converted into heat. That is that we want to study by thermodynamics, this conversion. Okay, so we just want to apply thermodynamics for chemical system. That is, for chemical system we will call it chemical thermodynamics. Okay, chemical thermodynamics, remember this term. Okay, chemical thermodynamics for chemical system, and we will discuss only chemical thermodynamics. Okay, because we are studying chemistry, so we just need to study chemical thermodynamics. So it is two types generally. First one is equilibrium chemical thermodynamics, another is non-equilibrium chemical thermodynamics. So equilibrium and non-equilibrium. But in our syllabus, only equilibrium chemical thermodynamics is contained. So we will only discuss the equilibrium chemical thermodynamics. And also, this will not be our part of discussion. Okay. So and also equilibrium chemical thermodynamics, it has two parts. So what are the two parts? The first part is macroscopic approach, and the second part is microscopic approach. Micro. So macroscopic approach of studying equilibrium chemical thermodynamics is that, suppose macroscopic term, that is pressure, volume, temperature, then number of mole, these terms. These are macroscopic terms. So these macroscopic terms are being discussed by in case of macroscopic equilibrium chemical thermodynamics. And microscopic, in case of microscopic chemical thermodynamics, we will discuss only the statistical thermodynamics or the thermodynamics which consists of statistical mechanics. Okay, so statistical mechanics in terms of thermodynamics, that is of course we call statistical thermodynamics, that we are not discussing here. Okay, that is the other part of discussion. Okay, so in JAM syllabus or it is not contained, or other in NET syllabus something like that, Maxwell-Boltzmann's statistical distribution thermodynamics, that is of course contained. But we only discuss here the equilibrium chemical thermodynamics. Okay, that we are going to discuss for JAM, NET and GATE examination. Okay. So now, what are the macroscopic, microscopic? So macroscopic thermodynamics, that we are going to discuss over here. Okay. Now let's talk about the macroscopic thermodynamics. So macroscopic thermodynamics. So in this full video series, it will be a video series because thermodynamics is a very vast chapter. So I want to discuss this in a series. So in this whole video series, today we will discuss about the basics of thermodynamics. Okay. So what are the things we have to discuss in the further videos? Okay. So that we will discuss in this video, and also some basics concepts we have to clear in this video. there are fourth law in thermodynamics, that is that we can discuss in the macroscopic part of thermodynamics. That is zeroth law, first law, second law, and third law of thermodynamics. The fourth law will be sufficient to discuss any nature experiences that we experience in the mother nature. That means, what are the law of thermodynamics? If I question you, then what will be the answer? The answer is the law of thermodynamics, or thermodynamics is the experience about the nature by human beings. Okay, what we experience in the nature. Okay, so experiences in the nature by human beings, that is going to be thermodynamics. Okay, the thermodynamics can be defined as like that. So now the question is, what is zeroth law, what is first law, what is second law, what is third law? So I will discuss individual law in the later section, but now I just want to discuss, I just want to tell you what are the things that we have to consider as zeroth, first, second, third law. So in case of zeroth law, what happens? We just only get, say, suppose zeroth law says, suppose A is in equilibrium with B, B is in equilibrium with C, then we can say A is in equilibrium with C. This is the basic concepts about zeroth law. What about first law? First law is says that work and heat, the conversion is possible. So the conversion between work and heat is possible in case of first law. In case of second law, what says? In the first law, it says the work and heat conversion. In the second law says the direction of that conversion, okay, or the conservation of energy, the direction, and the spontaneity. The process will be spontaneous or the process will not be spontaneous. That can be discussed through second law. And from third law, we can what we can discuss. Third law says it's quite easy that at 0 Kelvin temperature, everything will got iced. Iced means if you have seen the movie Ice Age, the cartoon movie, Hollywood cartoon movie, then what you get, everything got iced. And here also in the third law says at 0 Kelvin temperature, that is theoretically in the macroscopic term is not possible, but theoretically in the statistical term it's possible. And theoretically it says that at 0 Kelvin the A's will be ices, everything will be got iced. Okay, so that is the third law of thermodynamics. We will discuss every law in the in detail in the later section. So now the question is, to discuss all these thermodynamic terms, thermodynamic laws, we have to consider some thermodynamic terms and have to define them. Okay, we have to consider and have to define all those terms. Then we can easily get the idea about the what kind of laws, how the laws are generated, how the laws can be explained. Okay, so the first term that is about the system, that is about thermodynamics, is system. That is related system, surrounding, and boundary. So these three terms are related to each other. That's why I am writing three terms at once, at a point. Okay, so at a time. That's why suppose this is system. So system, what do you mean system? Suppose take a glass of water. Okay, take a glass of water. So that will be the system. Then except the glass of water, the other things that will be surrounding. So if it is a system, then this will be surrounding. Okay, this is system, surrounding, and this will be the boundary. That is the glass, the wall of the glass, that will be the boundary. Okay, so system, surrounding, and this will be the boundary. So in between system and surrounding, boundary will be present. Okay. Now we will discuss about the boundary. So what kind of boundary is, what are the possible number of boundaries or the different type of boundaries that are possible. Okay, so boundaries basically three types. What type of boundary, what will be the number of types of boundary? So the first type is 1, 2, and 3. First boundary is dithermal boundary. Dithermal boundary. Second is permeable boundary. Third is adiabatic boundary. Okay, dithermal, permeable, and adiabatic. So what is dithermal boundary? Dithermal boundary means the boundary, suppose this is a boundary, this is system, this is surrounding, just rough case. So if this is system, this is boundary, this is surrounding, dithermal boundary will allow only the energy from system to surrounding or surrounding to system. Only allow the energy exchange, energy transfer. Energy means suppose heat transfer. For example, if you take a glass of water, hot water, then water, if it's a steel glass, then stainless steel glass, then heat can be passed through the wall of the stainless steel glass and can reach to the surrounding. Okay, So this kind of conversion is possible in case of dithermal boundary. But in case of dithermal boundary, mass, that is the matter, that is the water, if the bottle is sealed means the water vapor cannot be passed, but the wall is not thermally bounded, that is wall is thermally permeable. Okay, so that's why energy can transfer from system to surrounding. But if the system is totally locked, then matter, that is water in that glass, cannot be passed as vapor from the system, okay, from the glass of water, if it is closed with a cap. So now system to surrounding conversion, but the energy conversion, but the matter conversion is not possible. That will be the dithermal boundary, that is dm equals to 0. Energy of matter will be 0 or mass will be 0, change of mass will be 0, but change of energy will not be 0. I mean change of energy will be possible between system and surrounding through the boundary. Okay, this will be the dithermal boundary. In case of permeable boundary, both energy and matter transfer can be possible. How? Say the system, like the glass is open, the cap is not present, then what will happen? Water can be passed from the system as vapor, that is mass from the system can be passed to the boundary, or like boundary likely to be a boundary like porous boundary. So in that case, that water can easily convert to goes from system to surrounding. Okay, in case of porous boundary, but that kind of boundary is called permeable. That means in case of permeable boundary, energy can pass through the boundary and also mass can pass through the boundary. Okay, mass change is possible, energy change is possible. That is possible, that means not equal to 0. If it was not possible, then that will be equal, that is initial energy or final energy will be equal. So that's why the energy change should be 0, but here energy change is occurring, so energy and mass change is occurring, so that's why they are not equal to 0. In case of adiabatic boundary, what will happen? Neither energy not mass change, neither energy not the matter passing through the boundary from system to surrounding is possible. Okay, so that's why energy change, matter change is 0. Okay, so this is the different three kinds of boundary. So now let's talk about depending upon this boundary, let's talk about the systems, different kind of systems. So now we have to discuss about systems. So similarly, you will get three system, 1, 2, 3. First system is closed system, second system is open system, third system is isolated system. So for closed system, boundary will be dithermal, or inversely we can say, in case of dithermal boundary, the system will be called closed system. That means energy can pass but matter cannot pass. In case of open system, the boundary will be permeable. Okay, permeable. For permeable boundary, the system we will call the open system. That is, energy can pass and also matter can pass. Okay. Next coming isolated system, that is adiabatic boundary. So neither matter nor energy can be passed to the boundary. Okay, so that kind of system we will call as that kind of system we will call as isolated system. Okay, so these are the systems. So for example, closed system, that is hot water in a closed beaker, that is closed system. That is wall will be heat so that the wall, that is the stainless steel type glass, so that heat can be transferred from system to surrounding. For open system, it's a volatile liquid in a beaker without any cap. Third system, isolated, that is the thermoflask, you know about this. So these are the different kind of systems depending upon the boundary. So now let's talk about some properties about the system. So we have to understand the whole system, surrounding and boundary, we have to understand the properties of the system, and then we can apply these properties to study the thermodynamics. So first property is extensive property. Remember, extensive, and the second property is intensive property. Remember, these two properties are very important, so just try to understand. So extensive property means the property which is dependent on mass dependent, and intensive property is not mass dependent. Okay, so extensive property, just take a copy and write all those points what I am saying. This is first point. Second point, extensive property is additive. Additive means suppose two extensive property you have to add, then we will get another extensive property. Okay, like that. It's not additive. Okay. Third point is we just want to give you some example, that is the volume, then density of a solution, then energy, then heat capacity, then all thermodynamics, that is E, H, S, A, that is Hellman's free energy, Gibbs free energy, everything. All the thermodynamic properties are extensive properties. But the intensive properties, remember, very important. Remember the examples, that is surface tension, eta, then refractive index, then molar volume. Remember, volume is extensive, molar volume is intensive. Then specific heat capacity. Heat capacity is extensive, specific heat capacity is intensive. Remember these two. Temperature, chemical potential, okay, chemical potential, like this. These properties are extensive, these are intensive. Then other examples are these. Most of the extensive properties are not inherent, but most of the intensive properties are inherent. Okay, so next point, last point is, if we do sum up to extensive properties, we will get extensive properties. But if we do the ratio, if we want to get the ratio up to extensive property, then the property will be generated, that will be intensive. So sum up to extensive property will be extensive, but ratio up to extensive property will be intensive. But ratio of or sum of to intensive property always will be intensive. So remember this last point, sum and ratio for extensive, sum will be extensive, ratio will be intensive. But in case of intensive property, sum and ratio will be, both will be intensive property. Okay. So this is about the system with intensive and extensive property. So now coming to another point, that is about important thing, that is a function. So there are two types of function in thermodynamics. One is state function, another is path function. So what is state function? State function means, say any system right here and another system right here. So it can convert from A to B, A state, B state. So the whole system, the value of change of function, suppose a function fx, the change of this function, if we change the value of function, then the change of this function will be dependent upon state A and state B. Okay, not the path, how we can go from state A to state B, that will not be dependent. But in case of path function, suppose here is I am in IIT Roorkee, here IIT KGP, and here another is IIT Roorkee. So I can go to IIT KGP to IIT Roorkee from like Kolkata. First I go to Kolkata, then take a flight from there and go to IIT Roorkee. Then I can catch the train from Kharagpur station, or I can go to the South India. That will be odd, looks like odd, but if I go to South India first, then I go to IIT Roorkee taking a flight, then that will be another path. So the function, that will be this kind of path dependent. If we go different path, we will get different result, like that. So that is path dependent function, and some functions are state functions. So what are the state functions? Most of the thermodynamic functions are state functions, that is energy, enthalpy, then entropy, then Hellman's free energy, Gibbs free energy, all functions are state functions. Path functions are, remember two, work and heat, Q and W. Work and heat are path functions. We will discuss these two functions in the later section. Okay, so these are state functions, these are path function. Another property of state function is, like, state function follows the exact differential or perfect differential, that is 1 to 2 state, change of a function m, that is dm. So what will happen? That the integration will be m2 minus m1, that will be delta m. Okay, so that is the formula, the exact function, that is the formula of exact function. Okay, but in case of path function, the function will not be exact. That means 1 to 2, suppose a function z equals to z2 minus z1, this will not be this, or not is equal to delta z. Okay, so this 1 to 2 state dz we cannot write like this. Okay, the function only we can write about as z. Remember this one. We have to write, in case of path function, the 1 to 2, because that does not depend upon the state 1 to state 2. It is path dependent. That is why 1 to 2 state we cannot write like this. We have to write just 1 to 2 dz equals to, will be what? Now will be only z in case of path function. Okay, we will discuss this in the example section, where I will prove the work, that is a path function. Okay, so that will come later. The next point, last point is that is, we can say, next point is, say there is the cyclic integral of any path function. Suppose dm will be 0, but cyclic integral of any cyclic integral of state function will be 0. Cyclic integral of any path function will not be 0. So if we take dz function, that will not be 0. Cyclic integral 0, not equal to 0. And the last is Euler's condition of exactness. So to be state function, Euler conditions of exactness to be fulfilled. So what is Euler's condition of exactness? That is, if m is a function of f of xy, and here in case of path functions, if z is a function of f of xy, then if we if the function follow the Euler's condition of exactness, then the condition will be like d square m del square m by del x del y equals to del square m by del y del x. Okay, this is the Euler's condition of exactness. So state function follows this condition, but path function does not follow this condition. That means del square z del x del y is not equal to del square z del y del x. So this condition is not fulfilled by path function, but state functions follow this condition. Okay, so this is all about the first part of this video, and in the next part of this video series, we will discuss about, we will prove one function as path function, then we will discuss about the cyclic rule, then we will go to the zeroth law, first law, second law, and different thermodynamic processes. That is, for example, isochoric process, isothermal process, what are the definition, what is reversible process, very detailed study, not the light study. I will discuss very detailed study, and for that you have to subscribe this channel, and of course push the bell icon you have to get the notifications when I upload in the tomorrow in the second lecture of this series. Okay, so just I will also discuss the mathematical formulation of each and every point, each and every system. Okay, so if I discuss the zeroth law, I will define, and then I will show you the mathematical formation of zeroth law. For first law, I will show you the mathematical formation of first law, and so on and so forth. Okay, so thank you. That's all about this video, and thanks for watching.